Hi everybody, in this video we are looking at the scalar product of two vectors, and this is also known as the dot product. Okay, last year when we were looking at vectors, we did lots of vector addition and vector subtraction. But that raises the question, can we multiply vectors? Well, yes, we can multiply vectors. But the thing about vector multiplication is that it can mean a few different things. First, we've got the dot product, or also known as the scalar product, and it's represented imaginatively by a dot. And we've also got the vector cross product, also called the vector product, and it's denoted by a multiplication sign. Okay, so we've got the dot product and the cross product. What is the dot product? Well, the dot product of two vectors gives us a scalar. Okay, a scalar, remember, a scalar is just a number. It doesn't have direction. It's just a number like 2 or 3 or -5. Cross product delivers us a vector. For example, something with i's and j's, and a product. The cross product will give us something with magnitude and direction. Now this year we are only looking at this one here, the dot product of two vectors. Next year in year 12 we go on to look at the cross product. But the cross product is actually not defined. It doesn't exist for vectors in the plane, like vectors just with I and j, two-dimensional components. For the cross product to work, we need 3D vectors. This year we are looking at the dot product, also called the scalar product. It is represented by a dot, and it is really important that you use a dot to denote it and not a cross, because a cross product is something very different. Okay, let's have a look now at what the dot product is. If I have two vectors, and vector 1, A, is A1 and A2 like that, and vector B is B1 and B2, we could denote vector A then as A1 lots of I plus A2 lots of j, and similarly for vector B. What does it mean to do the dot product? Well, it's actually really easy. A dot B equals A1 B1 plus A2 B2. Okay, so if vector A is 3i plus 4j and vector B is -2i plus 5j, A dot B, how do we find that? Super easy. We say that one times that one, 3 times -2 plus 4 times 5. And you'll notice how that has generated for us a scalar, just a value. It is no longer a vector. The dot product, or the scalar product, will give us a scalar value. So all I do is I say that number times that number plus that number times that number. And remembering to keep an eye on our signs so that we don't make silly mistakes. Now, one of the awesome things about the dot product is that it has a geometric definition as well. So A dot B is equal to the absolute value of A, that is the length of A, multiplied by the length of B, multiplied by the cosine of the angle that is in between them. So if I have vector A here and vector B here, I can find the dot product by taking the length of that, multiplying by the length of that one, and the cosine of that angle. But here's something magic. What about if I have the vectors in this form here, in this Cartesian form, and I want to find out what the angle is in between them? Well, here's what I do. I use the process I showed you before. 3 times -2 is -6, plus 4 times 5 is 20. And I can say that that equals, well, the length of vector A, well, I'm going to use Pythagoras. 3 squared plus 4 squared is 25, square root of that is 5, multiplied by the length of B, again Pythagoras there will give me, that's going to be root 29, multiplied by the cosine of the angle in between. Now I'm wanting to find out what this theta is, and I can do that quite simply from here. just by using a little bit of algebra. Using my calculator, that comes out as 58.67 degrees. Now let's just have a look and see if that makes sense graphically. Well, this one here is vector A, 3i plus 4j, and this one over here is vector B, negative 2i plus 5j. Now, does it make sense that this angle in between here is about 58 degrees? Well, yeah, it is. So we can use this equality here to find out the missing bits. Okay, we've got another question here. We are told what points A, B and C are, and then we need to find what the magnitude of angle ABC is. So we're after this angle in here. Now to do that, I've got a vector that I'm going to put in here and then a vector there. Notice here that both of those vectors are starting here at the same point and they're going off from there. So this first vector here we will call vector BA, and this one is vector BC. Okay, what is vector BA? Well, it's going to be A minus B. 1 minus 2 is negative 1. 3 minus 1 is 2. What is vector BC? Well, it's going to be C minus B. 1 minus 2, and minus 2 minus 1 will be minus 3. Now, just to make the notation a little bit easier, I'm going to just call this one here vector E and this one here vector F. Well, our dot product rule tells us that E dot F equals magnitude of E by the magnitude of F by the cosine of the angle in between them. Right, well, I can work out E dot F, just saying this one times this one, plus this one times this one. And that's going to give me there negative 5. Okay, for the norm of E, all I'm doing here is Pythagoras. Remember, it's going to be the square root of this one squared plus this one squared multiplied by magnitude of vector F, 1 plus 9, cosine of the angle in between them. So that's going to come 5 times 10 is 50, square root of 50 by the cosine of that. I do a little bit of algebra there, and then that comes out that theta is actually equal to 135 degrees. Now I'm just going to go back to my diagram. Does that look right? That angle there, 135, yeah, that looks right. So what are we making sure of? We're making sure that our vectors both are starting together at that point, and that will give us the angle in between. Okay, we might just pause here briefly to have a look at a few properties of the scalar product. Well, the first one, A dot B equals B dot A. This one is called the commutative property of multiplication, and we know it well, like 3 times 4 is the same as 4 times 3. But here with the dot product, you just try it with a few numbers and you can see quite simply why that one will work. We've also got the next one over here. This one here is the distributive property. You'll know this one if I have 3 lots of x plus 2, 3 lots of x plus 3 lots of 2. It works the same actually with scalar multiplication of vectors, so the scalar product. So if we have vector A, lots of dot B plus C, that equals A dot B plus A dot C. Next one up here involves scalar multiplication. So if I've got this k as a scalar, it's just a number, 3 or 4 or something. It doesn't actually matter when I do that multiplication. I might like to apply it to vector A first or to vector B first. Now notice, of course, we can't apply it twice, and if you just think about how numbers work, you'll understand that. So if I've got 3 lots of 4 times 2, I don't say 3 lots of 4 plus 3 lots of 2, do I? No. It doesn't work like that. So I could either say 3 4s are 12 times 2 is 24, or I could say 4 2s are 8 times 3 is 24, or I could even say 3 2s are 6 times 4 is 24. So just with a scalar multiplication, just like with normal multiplication there, we can do that whenever we want. We just multiply the scalar through once. This one over here, a dot 0 equals 0, pretty self-explanatory. Now the most important one of all of these here is this one. If the vectors a and b are perpendicular to each other, then a dot b is equal to 0. Let's think about why. If we've got, remember, a dot b is the length of a by the length of b by the cosine of the angle in between. Now, if these vectors are perpendicular, that means that they're at a right angle to each other. Here's our plane here. What is the cosine of 90 degrees? It is equal to 0. So if this part here is equal to 0, then the whole thing is equal to 0. Now this one works both ways. So if two vectors are perpendicular, if they're at right angles, then the dot product will be 0. But if the dot product is 0, then they are perpendicular. That is proof that they're perpendicular. The one exception is if one of the vectors is a 0 vector, obviously. But apart from that, if the dot product is 0, then you know for sure that that they are perpendicular to each other. If you've got two non-zero vectors, a and b, then vectors a and b are perpendicular if a dot b is equal to 0. Okay, finally, if we have got two vectors in polar form, well, then it's really easy to find the dot product. Let's just think about it. Remember, let's just use a and b. A dot b, length of a by the length of b by the cosine of the angle in between. Well, let's just say that vector a is, say it is 3 units long and it's at an angle of 30 degrees, and vector b is, let's say it's 2 units long and it's an angle of 45 degrees. So we've got a situation like here, we've got 30 degrees like that would be vector a, and vector b, 2 units long, 45 degrees, okay? So what is the angle between them going to be? Well, it's going to be 45 take away 30, isn't it? So the angle between those is going to be 15 degrees for that bit there. And how do we work out a dot b? Well, all it is we already have the length of a and the length of b. That's those things that are there. So it's r1 times r2, and then we subtract the vectors to get the length in between. 45 minus 30 is 15. So cosine of 15 by 3 2's are 6, and that will give us a dot b. And let's just do a couple of these to practice. What's the angle between these vectors? Well, these first ones, it's going to be 4 times 5 is 20. Cosine of, well, 60 minus 30 will be that. Can you see here, if they're in polar form, the work's pretty much done. The second one, a dot b, is going to equal that one times that. Cosine of difference between these, it's going to be 120, take away negative 30. That's going to be 150, isn't it? And just use my calculator for the answer for that one. The next one here, a dot b is going to equal that times that. Cosine of the angle in between. So look, I normally just get the big one. 60 take away negative 20 will be 80. And that equals 15 and a bit. Okay, you're now ready to do the exercises. We're working from Cambridge this year, and Cambridge I think has exercises of really good length. It's exercise 6D that you're working on, and I want you to try and see if you can do all or most of the questions. So if you leave some out, don't leave out whole questions. Like for example, in question 1, you might do 1A, B, E, F, but make sure you do at least some of all of them. Okay, thanks. As normal, please contact me if you've got any issues.